So welcome everyone. Today is the fifth day of Coherence, and we are here with our beloved Professor Parthasarathi Majumdar with his lecture. So it has been a month. We started our journey in Coherence as a part of popularizing science, popularizing physics, to enjoy physics in this toughest time of this pandemic. And it is also another issue that is called Rebuild Bengal. In this cause, we are trying to help and we are trying to provide some kind of solidarity with the enthusiasts who are tirelessly tirelessly working to the devastation and causes occurred during this pandemic and this Yaas super cyclone, which was hit uh, 2 months earlier in the coastal area of West Bengal. So let's welcome Professor Parthasarathi with us. Hello, sir.
Thank you. Hello.
Thank you, sir.
Am I audible? Yeah.
Yes, sir. Yes, sir. You are audible. Sir, thanks a lot for coming with us in this seminar and in this occasion. So, if you have any, yes, if you want to share any experience or any thoughts on our program, etc., you can share.
Oh,
sir.
yes. I would like to say that I'm very happy with the way that the Physics Forum Kolkata has organized this coherence, and also in the way it has participated what it calls the rebuilding of Bengal, because after the pandemic and the super cyclone Yaas, which destroyed large parts of the state, rebuilding has become necessary. And it's obvious that the government alone, despite its best efforts, may not succeed completely in this effort because it's a gigantic problem. And therefore, the participation of young people like the Physics Forum and other youth organizations, which have undertaken this task, this very essential, necessary task, extremely laudable from our point of view. Although we have not been able to participate directly in this effort, the best we could do was to contribute some contribution towards meeting the expenditure of this great effort. So I think this is the effort that the Physics Forum Kolkata has made towards repairing the damage caused by the natural disasters. In addition, I would also like to thank Orijit especially and the whole team, Physics Forum Kolkata team, for having undertaken the task of organizing this harmony of excellence, as they call it, where physicists and other scientists come together to discuss with undergraduate students their expertise. Now, this is very essential because it often happens that college students do not have this opportunity to know about what is happening. And it is with this point of view that I decided that I must appeal to undergraduate students and have something catchy in the title. Of course, I'll explain the title as I go along. So I would like to laud again, I would like to congratulate the Physics Forum Kolkata and Orijit in particular for this effort.
Thank you very much, sir, for your response. And we are trying to do these all things, and without the help of professors like you, it is not possible for us to organize this kind of seminars and webinars. So I think you should go on your slides, and that will be better. And the students are waiting for your lecture. Very long day.
Okay, so, thank you.
Now the screen is yours.
Yeah, okay, sir. Thank you very much. Thank you. So if please let me know if the transmission stops at some time. Okay.
Sure. We are here in the wings.
Right. Okay. So you might all be surprised that I have this title called Black Holes in Water and in Sand. Many you've probably seen pictures like this on television, or maybe seen them in the newspapers. And so, they absolutely don't look like anything in water or sand, and they're not. This picture, the NASA image based on data from the Event Horizon Telescope observations, has to do with has to do with a gigantic a black hole which is several crores, hundreds of crores the size of our sun in mass. That black hole is, well, this is the other earlier picture taken by the Event Horizon Telescope. It's in the galaxy M87, and this is a complex picture because although it looks like there's a black thing in the middle, by no means should we assume that the black thing in the middle is a black hole. Here also, the black thing in the middle, surrounded by the very beautiful orange light, is not a black hole. Okay, that's the first thing to realize. The orange thing is also not something that you can see. It's a false color image. It's an image which takes electromagnetic radiation and then colors it to make it visible. Now, you all know that electromagnetic radiation could be from X-rays and gamma rays down to radio waves, and this one is in microwaves, and therefore it cannot actually see it. It's all drawn by hand. But the details of the picture are correct. The distribution of intensity that this picture depicts is all correct. So what is the black thing in the middle? Well, to explain what is the black thing in the middle, it is perhaps best to go back to this picture, which of course is not a photograph, it's an artist's impression. Now, what you see here on the right-hand side of the picture is my a little arrow visible? This arrow? Orijit, hello. Can you see this arrow? Hello, Orijit, can you see the arrow?
Yes, sir. Wait, sir.
This arrow, when I move it around? Okay.
Yes.
So this would be like the pointer. So the blue thing here is what is called a blue giant. It's a gigantic star, but it's an ordinary star. And it's an ordinary star close to a black hole. So this thing is a depiction of a binary. Binary meaning a combination of two objects, one of which is a regular star, but it's gigantic. Gigantic, namely that it's again crores and crores times bigger than our sun. And reasonably close to it in the galaxy, in the constellation Cygnus. Okay, Cygnus is a constellation in the Milky Way, and in that constellation there is this thing which is called X1. Now, what this thing is doing is to grab material and light and everything, and you can see that it forms a disk as it goes around. As it goes around, it forms like a disk. And this disk is called an accretion disk. Now you can imagine that if we are somewhere here, then as it goes around, then all the light that travels here may not reach us. So if there is a telescope on this side, then you can see that if the light is coming from here, some light will be absorbed here. Now, this is where the artist has depicted that there is a black hole which is absorbing the light. So if your telescope is sitting here, then you can see immediately that there'll be a shadow, there'll be a region from which there is no light, although that region is sort of like this shape, but it's really not this object at all, this black hole at all. It's caused by the fact that the gravitation here is so powerful that not all the light from this side can reach this side. That is the whole idea. So here, when you see M87 or even this NASA image, this is really the shadow. This is the black hole shadow. It's a region which is created by the fact that, this accretion disk, not all the light from behind the accretion disk can reach the observer who is in front. Okay, that is the idea. So now you realize that a black hole, of course, is something from which nothing can escape. That is known, right? And sometimes mistakenly, at the higher secondary level, you are asked questions related to escape velocity. And that is often used to say that a black hole has the escape velocity equal to the velocity of light. That whole explanation is actually wrong because in Newtonian gravity, you cannot have black holes. It's a very strict result that there's no possibility of a black hole in Newtonian gravity. And there are many reasons for it. I can go into a discussion of that alone. That's good physics right there. But the most important thing to realize from here, especially for all the students, is that to understand black holes, there's no alternative but to understand the general theory of relativity. So you have to understand general relativity, we call it GR, in order to be able to understand what a black hole is. That takes some amount of math training and some amount of physics training, and that is why learning GR happens late at the MSc level. You usually don't learn general relativity at the BSc level, although I think it is possible to teach GR at the BSc level. Indeed, there are lovely books now which teach GR at the BSc level, at the undergraduate level, abroad. So if you're really keen, we can discuss it as a project, how to understand black holes. So this is, as I said, an artist's impression, an accretion disk, and there are lots of features from this accretion disk. For instance, you can see these pair of jets coming out from this region. Okay, they don't come out from inside the black hole. That's a little bit of a misrepresentation, but they happen fairly close to what is called the event horizon. So the event horizon, well, before I get to the event horizon, I figured that some of you may be quite young and may not even know what special relativity is. So I shall just focus a little bit of time on special relativity and talk about the space-time diagram of special relativity, which is the simplest way to understand special relativity. Special relativity is based on the concepts that there's something absolute about the propagation of light. So in this diagram, the blue lines with arrow represent the propagation of light into the future. Now, if you draw any line in between these two blue lines like that you could take as the axis of time, and this axis right here is the axis of space. So, of course, I've drawn time and only one direction of space. In reality, we have two more directions of space, because space, as you know, is three-dimensional. But I can't draw that, on this flat two-dimensional plane. So basically, this is just to show that if you're standing still, then also you travel in time. So that's what you're doing when you're standing still somewhere. Okay? On the other hand, if you're moving, then this is how you look. You're moving both in space and in time. And this pink line here represents any event seen by different observers. That is to say, observers moving with different velocities. So that's this diagram. Now, this diagram is fantastic because it tells you that outside these blue lines, for instance here or here, no information can reach you if you are inside. So there is already within special relativity the idea that not everything is accessible to you at every instant of time, at every location in space. However, if you wait long enough, then more and more things become visible to you. And that is why, these lines keep diverging, they are increasing in time. So although there is a kind of a restriction on what you can see outside, slowly with time and with more space coming inside, you can see more. Okay. Now here, because I don't have much time, I wanted to give you the idea of curved space-time. Now, these are the space-time diagrams I just discussed. In special relativity, all space-time diagrams look identical. Okay, so you can see that they all look identical, which is to say, we call it flat space-time. Flat, why? Because you can think of shelves like this going from left to right, and as if all these little cones are fixed to that shelf. So there are flat shelves which go like this. Contrast that to the diagram on the right. You can see that if there is some object with mass or energy, in special relativity itself, we know that mass and energy are equivalent. So if here there is something which carries mass and or energy. It need not just be mass, it could be some very intense source of light which carries no mass but has lots of energy. And then you can see in the vicinity of that, the events in space and time undergo a change because the light cone, the light frame, tilts towards the source of the energy. So there's a curving of the light cone. Now, this is perhaps one picture which indicates, as opposed to other pictures, you see, in many books and in many popular presentations, what you see here is a kind of a sheet which is bent because of some mass falling into it. But that is only spatial curvature. The important thing here is that not only does space get curved in the presence of something massive, but time also get delayed. For instance, if suppose you are here, okay, and suppose you are getting light from here and light from here. Now, because of this guy, if you now ask about the light from here, you can see that it's taking a long time. And so if this is your world line, you're just standing here, then you will receive light much, much later. Light from here will take even later to reach you, okay? So you see that there is a difference. On the other hand, if you're standing here, light from here will reach you at this point, light from here will reach you at this point. So you just follow the line and it goes there. But here, light takes a longer time because a light cone, this frame has actually bent. It has undergone a change in direction. It's been tilted. Okay? Because of this tilt, there's a tremendous impact on how space and time evolves in general relativity. It's very different from special relativity. Okay? And of course, it involves curvature because you can see that space and time taking longer means that the light cones here, in the presence of something causing gravity, cannot all be the same. Not only that, if you follow the path of light, follow here, 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 the light seems to be bending. It's one of the consequences of general relativity. Every trajectory, every line, every path of every particle must bend in the presence of gravity, including light. Whereas here in special relativity, it doesn't happen. Light just follows a straight path, right? So I wanted to explain to you this contrast. And if you now believe that we have a star M, okay? Now you have to think of this picture as time slices. So time is flowing in the vertically upward direction, and we are making slices of the time just to see what the space-time at a certain time would look like. So at this time, you can see that this gives you how space-time looks like. And the light cone, now I've drawn a cone here, is the same picture as before, same picture like this. These are, I have not drawn the cone here, but you can draw the cone, it doesn't matter. And you can see that as this shrinks, the star becomes smaller and smaller due to its own weight. The star will shrink because after its fuel, hydrogen fuel and other materials which provide its fuel runs out, there is nothing else that the star can do except shrink under its own weight. So that's called a dying star. A dying star will invariably shrink under its own weight. It will become smaller and smaller. But as it becomes smaller and smaller, the material inside it will become denser and denser. So you can see from here, light travels this path like this. But here again, you see, because the light cone is bent, because this has become denser, it's causing more curvature at this point. Light will take a longer time to reach. And now, when it reaches this size, you see, what happens here is if you look at the light propagating here, so light will always travel along these lines. So the light propagates only along this. So if you are an outside observer, you'll never be able to see the light coming from this point because the light will only go along this line. But the shrinking does not stop and it continues. The density becomes larger and larger till the density becomes humongous because the volume of the object has shrunk to zero. And that sometimes people call a singularity. But the boundary at which you just stop seeing the light from the object, this line, this surface here, H, is called the event horizon because there is no way that what is happening, any information from inside the event horizon will ever reach an outside observer. So just before that, around here, you can still get some information, but it will be very late and you have to wait for a very long time. But once the event horizon is formed, then basically the inside of this region, whatever is happening, is now off limits. You can never see anything coming from it. So you see, if light travels like this, any particle will also travel through through the light regions, which means like this. So everything will travel. So if you draw the light cone here, it's an even smaller light. So you see, the fact that black holes trap everything is a result of space-time geometry dictated by Einstein equation. So it's a result of general relativity. It cannot happen. It simply cannot happen in a Newtonian universe. Black hole is an outcome of general relativity. Now, I'm going to go ahead and switch to a different kind of black hole, something we call a Kerr black hole. Kerr is the name of a person who first wrote down this very interesting solution. So this is a black hole whose event horizon is not a stationary surface. Well, it's a stationary surface, but it's not a static surface. It's rotating. Now, when this happens, when the horizon rotates, something else happens to the space-time around the black hole. The black hole space-time undergoes a certain change. So here I've given you the artist's impression. So this here, this magenta surface, the boundary of the magenta surface is called EH, the event horizon. But you can see this light green thing, the elliptical thing around it. So what is this region? Well, this region is called an ergosphere. An ergosphere. This is a region, okay, which in some ways is like the event horizon, but in some ways it is not. Because just like I told you, once you enter the event horizon, you cannot come out. But you can indeed come out of this region. The only thing is, in this region, whatever strange things happened inside the event horizon of a static black hole will start to happen here. For instance, if a particle is traveling slower than the velocity of light, once it gets into the green region, it will start to travel faster than the velocity of light. So in special relativity, we say that time-like quantities will become space-like inside. Okay, those of you who study special relativity will know what space-like and time-like are. So whatever was space-like interval, if you locate now that space-like interval inside the green region, it will of course again be able to communicate to it, but it will be a space-like region. Which means that if you have a particle, so let me just show you another picture. So this yellow region is a black hole with the event horizon. The blue region outside is the ergo region, okay? And the presence of the ergo region is fantastic because it has new physical phenomena associated with it. The first physical phenomena associated with it was discovered by none other than the Nobel Laureate Sir Roger Penrose, and it's called Penrose process. It's a process of energy extraction from the black hole. Now that sounds very strange. Black holes seem to gobble up everything, and yet we are talking about here how to extract energy from a rotating black hole. Now that sounds absolutely strange, doesn't it? But here is how it might happen. This is conceived by Penrose. So what we have here is a particle carrying some positive energy E naught, which comes inside and enters the ergo region. As it enters the ergo region, what used to be positive energy becomes negative energy, but energy classically can't be negative. So So what it becomes is what you were calling energy, okay? Inside, once you're inside the ergo region, is a kind of spatial component of momentum. And all of you know that the spatial component of momentum can be both positive and negative. So that's exactly what happens. Okay. So let's have this particle come in, its energy becoming negative. I call the energy being negative, but that's within inverted commas. You know what negative energy means. Well, not all of it becomes energy negative. So inside the ergosphere, it undergoes an explosion. One part of the explosion carrying negative energy goes into the horizon. So that is the part which is E2 less than 0. But then we have the other part. Because this is less than 0, the other part, which indeed has positive energy, but now the positive energy, because there is negative energy which I have subtracted from here, the positive energy with which this can come out. See, remember I told you that the ergo region does not trap anything. So the positive energy particle comes out with a higher energy than what it went in. Now this sounds a little crazy, right? Because what about energy conservation? What about this? What about that? But if you are thinking in Newtonian terms, then the answer is actually very simple. See, this will only happen for a rotating black hole. So what we mean by this is that when the piece with negative energy falls inside the horizon, what it does really is to transmit to this object a little bit of the rotational energy of the black hole. So as the particle piece with positive energy comes out, it takes with it a little bit of the rotational energy, and that is the gain in the energy that one has. And of course, the price that the black hole pays is that it slows down in rotation. Okay, it slows down in rotation, and this process might continue so long as the particle is rotating, so long as the black hole is rotating. Of course, when the black hole is not rotating, this process will stop. Now, this, of course, is very difficult process. How do you actually make this process happen? Because you have to fine-tune the particle to come inside the ergosphere, break into two pieces, one which will have positive energy, the other which will have negative energy, and ensure that the negative energy piece is the one which goes into the horizon, the positive piece is the one which comes up. That's a tall order. It's good to think about it, it's good to work out the math, but it's difficult to have it realized in practice. So what came out from here is another way of doing it, but replacing particles by waves. You see, waves are wave functions which satisfy the wave equation, and when they satisfy the wave equation, it's a linear equation, there is the principle of superposition, right? So that's the wave equation. Excuse me, just excuse me for a second. Hello. Sorry, I'm at a lecture. Yeah, so you see what happens is, in this case, there's a wave. This is the wave equation, the D'Alembert equation. That's the wave solution in 3 dimensions, 3 space and 1 time dimension. But then there's a superposition. So the incoming wave may actually split into a reflected wave, which will go out of the ergosphere, and a transmitted wave, which will go into the horizon. And now what you find is that if you tune the frequency, okay, to be of this, which is m is an integer, which is like the azimuthal mode number, and capital omega is the angular velocity of rotation of the black hole. So if omega is less than an m capital omega, and you assume a boundary condition that the event horizon is reflectionless, nothing comes out of the event horizon. That is very reasonable. We know that to be true. Then we find that the amplitude of the reflected wave reflected from the ergo region, is actually bigger than the amplitude of the incident wave. And that, we know, is like saying that the reflection coefficient is bigger than 1. You are used to studying the fact that the reflection coefficient plus the transmission coefficient is equal to 1. That apparently is is what you study in quantum mechanical unitarity, electromagnetic wave reflection from obstacles, and so on. On the other hand, here, in the black hole case, there is this strange amplification which Penrose was the first to point out, and other people did this with waves, and they found that the same to be true. There is indeed an amplification. So you have a black hole, you send in a wave, which then decomposes into two pieces, the transmitted and the reflected one. So from the ergosphere, you find sometimes that the reflected wave comes out with an amplification. Okay, so that if it comes out with an amplification, it's carrying energy from inside the black hole, and that we call energy extraction. Okay, now the sad thing about it, however, is that this effect has not been observed in nature. It cannot be observed in nature because the energy that it can take out from any black hole is so tiny that it cannot be measured. So this is a bit like Hawking radiation. I'm sure all of you have heard about Hawking radiation. I'm not going to discuss Hawking radiation in this talk, but in Hawking radiation, you know that a black hole radiates energy, okay? And the energy can be, in principle, detected by an observer sitting very far away, okay? And the energy is such that it's a thermal distribution of energy which obeys the Planck law, and therefore you can associate from the energy distribution a temperature for the black hole horizon. Okay? That temperature is given by a geometrical property known as surface gravity. Now, this is what Stephen Hawking found in the 1970s, very, very strange and beautiful mathematics, and we all believe that someday it will be seen, but now we know that even for a black hole, which is like a stellar black hole, which has a mass that of the sun, the temperature is so low that it will be completely dominated by the 3 degree Kelvin microwave background temperature, and therefore you'll never be able to see it. So just like Hawking radiation, the super radiant scattering from a black hole, which I just described to you, this is also not observable. So we have beautiful physical phenomena predicted in gravitation theory, but we have no hope in ever observing these phenomena. Now, for any physicist, this is rather depressing, and therefore, some physicists thought that maybe we can set up an analogy in a different situation where one can mimic maybe Hawking radiation, maybe super radiant scattering in such a way that now we can make an observation. And that is what I'm going to describe to you right now. So we're going to now change from black holes, astrophysical black holes, to black holes which basically are fluid flows. They are fluid flows which behave in some respects like a black hole, but not in all respects. And in the respects that these fluid flows behave like black holes, we would like to argue that yes, the physical phenomena that we are talking about can indeed be observed. So this was motivated by, remember, these black holes in water or in other objects and other materials or using light or whatever. The subject of analog black holes, okay, came out because of our frustration that there is no way to observe beautiful physical phenomena like Hawking radiation or super-radiant scattering. Okay? Super-radiant scattering, remember, has to do with the energy extraction from a black hole using waves. Okay? So now, I describe to you the first ever black hole-like or black hole analogy that was proposed. This is called the Laval nozzle with water. So if you have water flowing through a tube, and if you do a constriction like this, then what turns out is that outside the water is flowing at a subsonic level, smaller than the velocity of sound. But if you take this thing to be very narrow, then it turns out that only supersonic velocity waves are allowed in this region. Supersonic velocity flow is allowed in this region. So this supersonic velocity flow cannot go back. Because of the way the constriction is arranged, it can never go back. There's another picture. So outside you have both sonic and supersonic. You have both subsonic and supersonic. But once it's inside, because it's constructed in such a way, there's no way that this can go back. So this is then acting like a horizon. This is like a horizon. Okay? This is like an effective horizon because we don't know from here, from this, what kind of fluid flow is happening. It's a guess. So this is like a horizon. It cuts off this region from the region where you are able to observe what is happening. So there is no fluid flow in this direction from here. Okay. Now, what I'm going to tell you is something very strange. This is something you see every day when you're taking a bath or you're taking you're brushing your teeth and washing your face. You see this draining sink. Your sink drains water like this. What you probably did not notice, or maybe you have noticed, is that the water goes in a kind of a rotation, okay, like a vortex. This vortex has smaller speed outside, and as you go nearer and nearer to this sink, the velocity increases very large, becomes very large. Okay. Now, believe it or not, this kind of a flow is extremely useful, okay, to picture what might happen with superradiant scattering. This might actually give us an acoustic black hole. So there we are having something very simple. I'll give you a better picture here. This is a picture where when the lab has created a vortex and used green laser light to illuminate the vortex. So you can see the vortex very clearly here. The vortex is also clear here. You can see that it's coming down here, entering like this here. So this region would be, well, very close to this region would be the horizon, and outside the region where it's rotating would be the ergo region. Okay. So the question is, can we then observe in such a flow of water? Okay. Can we then observe the kind of physics we're talking about, energy extraction? So let me go back and tell you how this came about. It was Bill Unruh and later reviewed by Matt Visser, who discussed fluid flows. So this is fluid mechanics, non-relativistic in the lab. This has nothing to do with gravity. Okay? So these are the fluid flow equations, the equation of continuity and Euler's equation. And we assume that locally we have irrotationality, so the velocity can be expressed as the gradient of a velocity potential. Now you might wonder, if you have this, then how are you observing the, 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 the vortices here? So the answer to that would be that the vortices are extremely localized. So these are local objects, and around that, this is certainly true. So we can indeed define this kind of a velocity potential everywhere, except maybe very close to the center of the vortex. And we are not going to approach the center of the vortex, because the center of the vortex, nothing interesting from our point of view will happen. But what will happen here is that now if I look at perturbation, so this zero subscripted ones describe a background flow, and I'm going to make a little acoustic perturbation, little meaning epsilon is small, in the velocity potential, in the pressure, and in the density. Okay? So if I make this perturbation, we find that the same fluid flow equation mathematically has a dramatically different form. Now, why this thing happens is a miracle. It's a kind of a miracle, but it's a mathematical miracle. You begin to see that you have a kind of flow which is exactly like what will happen in a curved space-time of 3 + 1 dimensions to a scalar field. So the acoustic perturbation psi1, acoustic perturbation in the velocity potential, satisfies the D'Alembert's equation in an effective metric, a metric which is just like the metric of a rotating black hole, or maybe like the Laval nozzle I showed you. Now this is so strange. It was found by Unruh that this does happen. Okay, and since then people got very excited because they wanted to create a flow which is which is described by this metric to see if indeed some of the properties of black holes can show up. Okay? And what I mean by a metric, of course, is known that it's a relationship between space and time, which I've written like this. So the very fact that you have these objects here means that this is not a flat metric. Rho zero and Cs is the velocity of sound described by the derivative with respect to density. Okay, as always, the Cs squared is del P del rho. And this tells you that we have something strange. We started off with something which was perfectly Newtonian, flat space-time, no relativity at all, not even special relativity. And yet, if you look at the whole thing from the point of view of the acoustic perturbation, the acoustic perturbation does not see the space-time as you and I do. The acoustic perturbation, the acoustic ripple, the little blip that you send in, sees a totally different space-time. And that space-time is a 3 plus 1 dimensional curved space-time as in general relativity. This is something very strange, and it will take a little time for you to wrap your minds around it. It's not something easy. So let us continue with that, and then, we are talking about the draining sink, which I described earlier, the sink in your bathroom where you brush your teeth. There we have been able to write down explicitly the metric. It's of course in 2 plus 1 dimensions, two-dimensional, because the space there you see, if I just go back to that picture, all the vortices, you see the vortex is in 2 dimensions really. The third dimension is just continuation. Here also the vortex here you see is in 2 dimensions. Here also the vortex is in 2 dimensions, right here. 2 dimension, 2 dimension here. So what we have, amazingly, is you can extend it to 3 dimension by just putting the vortices on top of each other, but actual vortex is in 2 plus 1, 2 space and 1 time dimension. And it has the, if you look at this thing, then I can't do the math right now, but it's easy to see that this is a rotating black hole. So this is the analog that the acoustic perturbation sees. You and I cannot see this. You and I cannot see this metric, cannot see this geometry. This geometry will be only visible to the acoustic perturbation. So unless you're a little bacteria or something in the acoustic perturbation, you will not see it. But it's clear that it has exactly the geometry of a rotating black hole. This is the horizon, and this is the ergo region. So we have all the trappings, all the properties, okay, of a rotating black hole. Remember, if you go back a little, yeah. So you have the horizon inside and the ergo region outside. And we need the ergo region for energy extraction. I already described that too. So the question is now, given that we have this bathroom sink, which is displaying characteristics of a rotating black hole in 2 plus 1 dimensions, it has a horizon, it has an ergo region, can we then anticipate that there will be superradiance? Okay. This is a very important question, and I'm happy and proud that Showman, Boschak, and myself were the first to look at this question. Before that, people had worried about Hawking radiation, but they had not worried about acoustic superradiance in a draining sink. We were the first to do it. And we found that the math is very, very simple. I won't get into it, but you have to just apply some properties of the Wronskian. Believe that, again, the acoustic horizon, okay, is reflectionless. So if you use those properties and use the same kind of tuning, see this tuning, omega less than m omega h, remember that this tuning is exactly the same for standard gravitational, yeah, right there, see? So it's the same kind of tuning. By tuning, I mean you have to keep the frequency in that range. If you keep the frequency in that range, you indeed find that the reflection coefficient is bigger than 1. So you have energy extraction. So we predicted that in 2002, 2003, and much later in 2012 in the University of Nottingham, a group of Silke Weinfurtner were able to make this observation. Now there are still debates, but Weinfurtner, the lady who directed the lab where they observed this in water, claim that indeed there is super radiant scattering happening inside the vortex. The vortex pictures I showed are from Nottingham. These are from Nottingham. Beautiful pictures using laser light, green laser of vortices in water. Okay. So what was it? We were able to, so this is again by laser light, they were able to show in 2012. And now I think it's fairly well established that indeed the phenomenon which you could not see in nature, in astrophysics, is actually now observable in the lab. In the lab of Silke Weinfurtner in Nottingham, they have actually observed this phenomenon. So acoustic superradiance, just like we predicted, does happen. Very recently, I came across this paper. Now, they have done a very ingenious experiment. So what they have is a kind, so they say that, well, don't worry about horizon, etc. It is enough to have an ergo region. So they have an ergo region set up by this rotating pad. Okay. And they have microphones here, this M here, microphones. So as they go on rotating, you see, you can then they simulate a rotating black hole, and through the application of waveguides, they're able to show that indeed there is an amplification. So this is using sound waves in air. The work of Cromb et al. I haven't digested all the details of this because it was very recent, but now Cromb et al., these people, they claim that indeed, yes, the phenomenon that Penrose had predicted can happen in the case of acoustic superradiance. Indeed, acoustic superradiance is now therefore a known phenomenon. Okay. So this is very nice that it's acceptable, it's proven, and it's for me and my collaborator Shomin Boshak, who is now a professor at ISAT Trivandrum. We are very happy that finally what we thought of in 2003 has come to be true. Okay. So this is what I want to tell you about black holes in water. If there is a question, if there is a short question or two, I can address them now. Orijit, is it a good time to answer some little questions, or should I do it at the end? Orijit? Hello, Orijit?
Hello. Yes,
Hello?
sir. Sir, I think I'm audible, sir.
Yeah, you are audible,
Hello.
yes?
Yes. I think the questions we should take the questions in the end, sir.
All right, very good. Then I'll continue. Okay, because
Yes, sir.
I'm now
Thank you.
going to change. I have about 10 more minutes, right? Or whatever, something like that.
Yes, sure, sir.
Yeah, so, well, I won't take 10 minutes, but I want to tell you about something that we have done very recently. Very recently. It's in fact still continuing. And I'm also very happy about it because we think we are the first to think about something like this. So what is it? Well, you can anticipate it that since I had mentioned sand in my title, I'm going to first talk about sand. So now the sand is so lowly, we don't even bother to think about it, right? But look at this. Look at this picture. Now, when you think of sand, you think of what? Solid? You think of liquid? You think of gas? What do you think of sand? How do you think of sand? But look at this picture. This picture shows you that only sand has been able to grasp this car, the front of the car, and hold it like a vice. So obviously, the sand here is behaving like a solid, right? It's like a solid. The car is stuck there. So a car won't be stuck in water or gas or something, right? So this very very large van being stuck in a sand dune means that the sand here is behaving like a solid. But look at this. Look at the top picture. The top picture seems to indicate to you that the sand is flowing like water. It's liquid, like the water in the sea. The sand is flowing like water. So it's like liquid, obviously. The same sand is behaving like a liquid. Or here, in a desert, when the wind blows, if you have seen Lawrence of Arabia, you would have seen a sandstorm. And look at this. Sand all over the place. It's blowing like a gas. Okay? So what is it? What is sand? Is it solid? Is it liquid? Or is it gas? And this is a key problem. This is a key problem for which the experts have defined sand, or indeed more generally, granular matter. Granular matter is supposed to be the hardest thing in physics. Now here there's a scale. Newton's laws, that's the easiest. We all know how to do that. Special relativity, oh yeah, we know that too. Quantum mechanics, yeah, we know that too. General relativity, yes. Sand is at the extreme of the degree of difficulty. That is because we don't know what it is. I mean, you would have never believed this, right? But how can sand be so difficult? I mean, after all, Bali, right? I mean, this is crazy. So why should it at all be very difficult? And you can see some properties coming out from here. If you try to dig your umbrella into when you go to the beach or something, then it's easier to dig if you want to just set the lower end just below the surface. But the more deeper you dig, the harder it becomes. Now, this property, the experts, there are lots of experts. Among them, I should mention a lady, Bengali lady, Bulbul Chakraborty, who is in the United States, Brandeis University. She's an expert on this. And I should mention that our interest was aroused when she gave a talk at Presidency University almost a year ago, slightly less than a year ago. She gave a talk on this. And we, who were in the audience, were completely mesmerized by the lecture because of the strange things she was telling us. Okay? And then I found from New York Times, the newspaper New York Times, that there they had this picture. Okay? I was sent this by a friend saying that, well, sand is the hardest thing. And you thought quantum gravity or general relativity, particle physics, all those areas are fashionable, or maybe something in condensed matter physics. Yes, this is condensed matter physics, if you wish, but it's condensed matter physics with a difference because you don't know what has condensed. Is it a solid? Is it a liquid? Or is it a gas? So the trouble we are talking about is something known as jamming. Okay? So what is jamming? Now here, if you have, let's say, a large volume with a small few grains of sand or any granular matter, then the grains are free to move. But if you reduce the volume, then of course the grains are going to be stuck. So this is called an unjammed state. An unjammed state being a state in which the grains of matter of sand are free to move, and the jammed state in which they're stuck. Like in a traffic jam, they cannot move anymore. So we say that, jam hoyeche, jam hor maneki. That means you can't move anymore. So when we're talking about the jam state, the sand grains cannot move anymore. So here is another picture of jamming. So this is a kind of a glass funnel or something where, everything was falling straight. And when the volume suddenly become smaller and smaller, this red line shows that there is a traffic jam. Okay? Now here is what in physics we call a phase diagram. Now I don't want to explain the whole phase diagram, that will take too long. So you can see that this axis here is temperature, this axis here is load, this axis here is 1 over density. Now let's start from the origin, 0 temperature, 0 load, and go along the density line. If you go along the density line, we find that the that this gray colored region is called the jammed states. That's where the sand is jammed. Okay? So that means that there is a maximum 1/density for which jamming will happen, which means that obviously if it's 1/density, there's going to be a minimum density for which jamming will happen at zero temperature and zero load. So there's a minimum density at which this happens. So when we looked at this picture, some of us, and that will include my collaborators, whom I'm going to show you right now, some of us said that, wait a minute, what if we did not think like most people do? You see, most people think of this as some kind of a force. The grains are exerting forces on each other, and there are chains of forces and so on and so forth. A very Newtonian kind of view. So we said, hey, wait a minute. What if we replace this view by a completely geometrical view, which we can borrow from general relativity? So this is the picture we had. This is the picture. It also gives you the names of my collaborators, Soumendra Kishore Rai and Pratyushabha Boral. Pratyushabha had just returned from the United States. In 2020, he had just completed his MSc. This year, he has joined first year graduate school in the United States. Soumendra is about to leave for the United States, again going to graduate school. This is Professor Ratna Pole, who is a professor in Presidency University. Okay, so these are my collaborators, and we were the first to propose that you can have a gravity way, gravity analog, as you wish, of thinking about granular matter. So, Orijit, can I have a little more time? 5 minutes maybe, or 10 minutes? I don't know. I started a bit late. Orijit?
Hello, sir.
Okay,
Yes,
now,
sir, you have time. You can carry on, sir. There is no limitation, sir.
okay, very good. Okay, thank you very much. So now we felt that, instead of talking about the forces, let us look at the geometry of the parts of the grains. This was an approach, you see, which was started by Amol Kumar Raychaudhuri. You've probably heard the name Amol Kumar Raychaudhuri. He was a very well-known relativist. He was a well-known teacher of Presidency College for many, many, many years. And he's a legendary teacher as well as a researcher. Now, Raychaudhuri was not dealing with sand, he was dealing with the problem of singularity in space-time. But we can borrow his methods. So I shall not talk about space-time here, I shall talk about grains. So let's say these are two grains, two parts, these are parts of grains, and time is now flowing in the vertically downward direction. So as they fall, you see, there's a possibility that they'll go around each other. So you can see that they go around each other. This blue spheres is basically a depiction of what happens at a certain time. So time, this is the first instant, second instant, third instant, and you can see that the trajectories, the paths of the particles go around each other. They go around each other and they go around each other. This is one situation. Another possible situation is that the paths of the particles do not go around, they go straight down, but they come closer and closer and closer. And by closer and closer, what I mean is the volume of the sphere continues to decrease. And you see, when this is very small, that means the particle trajectories are coming very, very close. This is another situation which is possible, in which the speeds of the particles along these paths are different. So as a result, you see what started off as a sphere is now deformed into an ellipse, and they also seem to be deforming into an even narrower ellipse like this, okay, as we go in time. Okay, so these are situations, well, these two situations, and here you find that the trajectories converge. So these all come from Raychaudhuri equation. They converge because curvature of space tells you to do so. Now here, of course, space is not curved. This is just flat space-time, Newtonian space-time. But we are going to imagine that if we take only these two trajectories, then the effect of the all other many, many trajectories like here is going to be very, very small. so many grains here. All these other grains are producing a kind of an effective curvature. So this is not real space-time curvature. It is like an effective curvature. You have to imagine things a little bit. All the other grains are producing an effective curvature in which our two test grains are coming closer and closer. So now a little bit of math, not too much. I'm going to tell you Raychaudhuri equation in words. You see, what Raychaudhuri equation tells you is that the rate of expansion. So here what you saw is more contraction than expansion. But the rate of expansion, if you take the reverse of contraction, that is expansion of the trajectories, is given by this formula. Now, look at this formula a little bit. It says that there is this twist squared term, then a minus of the expansion squared, minus something called shear. Shear is nothing but this phenomenon in which a difference in the velocities makes this volume deform. Okay? It's called shear deformation. Okay? And this last term, Rick, is for Ricci times velocity squared. This Rick is the Ricci curvature due to the other grain. So what we're imagining is a situation where the other grains are producing a kind of effective curvature. So you can see that the twist is basically the curl of the velocity. The expansion is the divergence of the velocity. The shear has to do with the differential in the velocity, how different they are. And of course, if you look at this one, then you can see that the expansion has to do with the rate of change of fractional volume. Rate of change of fractional volume. By fractional volume, we mean the volume occupied by the fraction of the whole volume occupied by the grains. It's also called packing fraction in condensed matter physics. So the rate at which the packing fraction changes is called expansion. If this is positive, we call it expansion. If this is positive, we call it expansion. If this is negative, we call it contraction. So actually, the simplest situation is where you set this to 0, you set the shear to 0, and you set the curvature 0. Then you only have rate of expansion is equal to minus expansion squared. This minus sign is very crucial because then that tells you that if you start off with initial expansion is negative, so initially if there was contraction, then you will have total infinite amount of contraction. Negative infinity of expansion is infinite contraction. And infinite contraction is what we call convergence of the grain parts. Okay? And that in optics leads to caustic formation. If you have studied optics, you've studied probably caustics, then you know that the caustic formation happens when paths converge. So what we are saying is that jamming is actually caustic formation. Jamming is happening because the paths are converging so hard that they can't move in. Okay? And this happens under the condition from the solution of the Raychaudhuri equation if the packing fraction decreases with time. So if the packing fraction decreases with time, that means if the density increases beyond the minimum. Now this is exactly what we had from this picture. Only when this is the 1 over density maximum, which remember is the density being a minimum. Only so the minimum density here, and then this is larger and larger density because it's smaller and smaller 1 over density. So the jam state will happen, okay, in the absence of any load or temperature, okay, only if the density increases beyond the minimum density. And this then checks out with the phase diagram at 0 temperature and 0 load. Okay. On the other hand, it's possible that there is a load. And then we can appeal to Einstein's equation, which says that the Ricci curvature, you see, is given by the stress energy density, okay, which is positive. So in that same equation, now take this to be 0 and the geodesic shear, this also is 0, then there are two negative contributions. Now, as a result of the two negative contributions, the packing fraction there could be a convergence and jamming for lower than minimum density. So even though there's an minus expansion term, there could be possibility that you will have jamming because of the external shear stress present, which turns on a Ricci curvature. You will have jamming, okay, for lower than minimum density. Again, this is observed. This is observed because of this picture itself. You see, if there is a load, on the other hand, then maximum one-over density need not be there. That is, minimum density need not be there. Take any point here, for instance. You can see that less than 1 over maximum density does the job. So that means that if there is a load, it is possible to have jamming even if the density is lower than the minimum value. Okay? But the prediction comes from Raychaudhuri equation, the prediction that we were the first to make, I'm sure, I think, well, I'm not sure, but I think, namely that you see in this equation, this is negative, all these squares means they are positive, this is negative, this is negative, this is negative, and only this twist is positive. And we are seeing that it is because of this negative thing that convergence happens, and that we claim is the reason for jamming. On the other hand, if there is twist, then of course it will act against convergence and therefore against jamming, right? So we make a prediction that if the twist is not zero, then there'll be an impediment, a sort of resistance to jamming. Okay? So if the grain paths in this picture can be made to twist about each other, these paths, suppose you rotate this funnel, rotate this funnel so the grain paths twist around each other, or some such experiment you can set up, then maybe you can show that because of that there is jamming is less likely. But of course, this paths of particles, molecules going around each other is a characteristic of fluids. So obviously, turning on the twist would mean that you are going from the solid jamming state to an unjammed fluid state. Okay? So that's basically the idea that we're trying to talk about. Well, the funny thing is that this has parallels in gravity in the work of Roger Penrose using Raychaudhuri equation right here. So we are talking about a trapped surface. A trapped surface is one from which light cannot escape. So these are the paths of light from a surface which is contracting, which I showed you at the very beginning when a star collapses to a black hole. So that's what's happening here. This is another picture. This is from Penrose's paper. This is an artist rendering. If you have the patience, you can see from here why this is a black hole. So there is matter which is collapsing, and then it forms a trap surface. By trap surface, it means that light will not be able to escape to the outside observer. That you can see if you look carefully at the little light cones. Light will never escape to the outside observer. So this is something which happens in gravity, and now we are saying that it is the same picture. So the same black hole formation is happening in the case of sand in granular matter under the condition of trapping, of jamming. So jamming and trapping, jam state as trap surface. That's the kind of thing we're trying to say. And we continue this to the case of shear jamming. This is something that my collaborators Shomindra and Tushabo and Ratna have worked out. That you can see some structures appearing. So the top panel, this is you begin with no jamming, and then you turn on a sheer external force, external stress, and we find these kinds of lines appearing. And in our picture, we again begin with no jamming, and then when we do, so we think of jamming by shear as a kind of contracting cosmology in gravity. So when we do the math, believe it or not, this comes out beautiful. Okay, so I guess I should stop now. I've taken a lot of your time. So effective and acoustic gravity hold a huge promise. There's a lot of work to be done. It's a field which is emerging and still a lot to be done. There is another field which is called acoustic gravity. phenomenon which I did not discuss. So Hawking radiation I did not discuss. I also did not discuss a lens steering effect, which is the dragging of inertial frames in a rotating black hole. We would like to see, we have already proposed this as a theoretical model, but we have no experimental situation where this can be seen easily. Okay? We have proposed active fluids, fluids with bacteria, to be the right places to look for lens steering phenomena, but that has not worked out very nicely. Maybe effective general relativity is a way to understand granular matter secrets, and indeed there are self-gravitating models of insect swarms which explain why locusts fly in a kind of group. Okay, so I should stop at this point and ask for questions, and I think I've more or less said what I want to say. So if any questions, I'll be very, very happy to answer.
Thank you very much for your amazing lecture, sir. Sir, there is a couple of questions. You explained it very well, so I think there is no much questions. If we have any questions after that, we will mail you
Okay,
those
so
questions.
shall I stop the presentation?
Yes, sir, you can stop
Then
the
I can
presentation, sir.
probably. Yeah, so, yeah, there. Okay. Yes, Orijit, what is the question?
Sir, wait,
Can
I
you
am
hear me,
trying to.
Orijit?
Yes, sir, I can hear you.
Yeah,
Sir, give me a couple of minutes. I am trying to figure out the question.
yeah, sure, certainly.
Okay, sir. So there is a first question from Ornov Sarkar. He want to know that how we can make a quantum black hole in laboratory.
A quantum black hole. No, I think, well, first of all, or no, I don't know what you mean by quantum black hole. If you are talking about a black hole in quantum theory of gravity, then of course that's a different matter because we are just dealing with classical gravity here. Okay? So,
I think the question is visible in your
yeah,
description
I
box.
can
I
see
can.
it. Yes, I can see it. Um, and Ramanujan's equations do not tell us about classical gravity, but they do have to do something with quantum black hole calculations. But then you have to talk about a quantum theory of gravity first. Okay, so it's a theoretical question. Here, you see, the main reason why we're talking about black holes in the lab is because there are phenomena which we cannot see astrophysically. Okay, and because we cannot see these phenomena, we have to discuss an analogy where we can do the experiment. That's the most important part. Okay, yeah, okay.
Okay, sir. Sir, there is a question from my friend. He want to know how in classical scenario negative energy interact with gravitational force.
Oh, no, like I said, you see, when you enter, when a particle enters the ergosphere, because everything inside the ergosphere, there's a change in the signature. So space becomes time, time becomes space. What that means is that energy, which is like time outside, becomes like space. So it becomes like a spatial component of momentum. So mathematically speaking, you have to think of energy inside the ergo region as, as a kind of spatial momentum. And of course, you know as a physicist that spatial momentum can have both positive and negative signs. So mathematically, energy cannot be negative. So what we say negative energy, we actually mean something like a spatial component of momentum. Okay, because there's a shift in time and space when you cross the ergo region, when you cross the ergosphere, the boundary of the ergo region. Okay.
Okay, sir. Sir, there is a question I'm going to show in the background in the
Yeah.
description box. His name is something Mr. Sarkar. I don't know his full name. So he has an interesting question. Can you see that question?
Yeah.
Like in
Like
spaceship,
in spaceship. Yeah.
I think he misunderstood because in spaceship there is no kind of vortex he's trying to say. So I think he's asking about any kind of plane or etc. That if the window is broken or anything, there is some everything is pushed out of the plane because of air pressure. So we can think the same scenario of the space-time black hole. He's trying to asking that.
Well, I mean, we are doing an experiment not in a spaceship, not in outer space, but on Earth. Okay, so we are talking about ordinary fluids like water or ordinary material like sand. So this is very, very common. This is so common that we, each of us can do this experiment. Of course, you will need expert help. You will also need a lot of very good equipment with laser pointer, laser light, and setup and so on. But you can do it. So this is very, very common. So the whole point is that we have very common situations where things behave like black holes. Okay, so it's a fluid flow. You see, the fluid flow traps certain high velocity sound waves. Okay, so supersonic sound, supersonic waves are actually trapped, and that is what we call a black hole. Or in the case of the rotating sink, they go in and they come out with an amplification. That is what we call super radiance. But it's happening in the lab. Even with the speakers and rotating speakers and so on, the picture I showed, it's happening in the lab. So this is nothing as exotic as being in a spaceship when the windows suddenly break and you're thrown out, which you see in science fiction movies. No, this is something much more common. You can do it in your lab, okay, at room temperature and pressure, okay, right.
So I have a question. I don't know it is okay or not. That
No,
you
every
talked about
question
the
is okay.
fluid.
Please ask.
Okay.
Yeah.
So you talked about the fluid analogy first. Then you transferred our talk into granular matters. So what
Yes.
is the typical advantage of considering the granular matter in the space of fluid analogy?
Oh, no. The two are actually quite different. See, in the case of the fluid analogy, we began with known equations. They were discovered by Euler 300 years ago, right? Euler equations or even Navier-Stokes equations, these are known for 200 to 250, 100, 3 centuries ago, we know them. The whole problem with granular matter is that we don't know what the basic equations are. We cannot write down an equation and say, okay, this describes sand. There is no such equation. Now you might find it unbelievable, but this is what we heard 1 year ago when Professor Bulbul Chakraborty came and gave us a lecture. It's absolutely amazing. You know, we think of
Okay.
advanced physics, we think of Higgs phenomenon, we think of this, we think of that, quantum gravity, what have you, and yet there is sand right in front of our house, and we don't know how to describe it in physics. It is not a thermal object, it does not undergo phase transitions, it is not a quantum object, quantum fluctuations are irrelevant. Most of the solids you know are quantum objects, these are not. None of the physics you know describes them. So that is why we as novices could hazard a guess. Let's try GR. Okay.
Okay,
When
sir.
novices can do something, that means the state of the art is such that it has not progressed very much. Ordinary condensed matter physics is very hard. I, as a gravitational theorist, will not try to do that. But in this case, we noticed that nobody really knows what's going on. There is no fundamental theory of granular matter, unlike, say, metals or semiconductors, for which beautiful fundamental theories exist. So that is why, you know, that the degree of difficulty picture which I showed, it's the hardest thing physics wants. You can understand what's going on in Andromeda, which is 250 million light years away. You can understand, you know, some Big Bang or something. You can understand inflation. You can understand many, many advanced things, but you do not understand sand. So this is just to encourage you that here we have a different approach. Check it out. Okay. Now, so far the world has not been encouraged to look at our approach. So this is something I want to share with your audience. One of the things Professor Ashok Sen, the great string theorist mentioned, one of the things that you must learn as a physicist or as a scientist is to deal with disappointment, despair. That when you say something, people are going to say, can't be true. And that is what we have faced. Even Professor Bulbul Chakraborty said, nah. Okay? So we are fighting, we are trying to persuade her. Because she doesn't know gravity, well, she doesn't work in gravity, and therefore it's very hard to communicate. Okay? But who knows? Maybe this will work. So this is the other thing, you can always try something out. You have the freedom to try and try something imaginative. Why not? And see if it works. Right?
Sure, sir. Yes, sir. Now, I want to know that you worked a lot in granular matter and the analogy of black hole in
Oh,
this
no, no,
field.
no, 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 no.
So,
Granular matter, I have written only one paper, the one I showed you. Only
oh,
one.
okay,
I
okay.
have my actual activity is gravity, is black holes,
Oh.
black hole physics, real black holes, not analog black holes. But I have done some work in analog black holes as well. Yes.
Do you get any kind of advantage in this granular matter analogy? I want to know that. In spite of fluid analogy, or there is all
No, no,
the fluid analogy is
disadvantage.
more.
It's disadvantage. It's much easier to do fluid analogy. I am in fact working with an MSc student right now on the fluid analogy. Okay, to see
Okay,
what
sir.
effect friction will have, viscosity, how viscosity will affect superradiance. That's something I'm working on right now. Okay, so fluid analogy is far easier. This granular matter, it's just a proposal. Who knows if it will be true? It's the first ever proposal in the whole world. Nobody has thought of this proposal. That is why people don't want to look at it. Coming from India, one Neeraj Chopra is that's what you got, right? I mean, not too many gold medals coming from India, right? So that's just like that. If you write a paper saying something entirely new, chances are that the world won't listen. So you have to struggle very hard.
Okay.
Okay?
Okay, so there is a question that is
Yeah,
you told about you told tell us that we are not interested in the vortex inside the vortex or near the vortex region.
yeah,
So one try to know that is there any possibility to inside the to be inside to understand the behavior inside the black hole analogy by the fluid mechanics equation near the vortex region or inside the vortex?
yeah. Actually, the vortex inside of a vortex is very well understood in fluid mechanics. And what we find immediately is that the inside of the vortex is nothing like a black hole. So it's
Okay.
only the outside of the black hole which behaves like a black hole. The inside of the vortex is what everybody knows, okay? It's nothing different from standard fluid mechanics. And that is a very good description already. So from the point of view of gravity, the inside of the black hole is not interesting. Whereas from the point of view of gravity, the inside, sorry, what did I say? From the point of view of gravity, the inside of a
He
vortex is
wants to
not
know that.
interesting.
Yes, yes.
But from the point of view of gravity, the inside of a black hole is unknown. You see, when I use the word singularity for an actual black hole, I'm talking about ignorance. Because whatever happens beyond the horizon is not something I can access experimentally, right? So the singularity in a black hole is hidden by the event horizon. So I have no way of knowing what is beyond the event horizon. And therefore that part is experimentally inaccessible. Whereas the inside of a vortex is very much experimentally accessible. So I can monitor, in fact, if you have seen tornado,
Yeah.
some months back there was a tornado near Noihati.
Yes.
Everything inside the tornado was mapped. If you look at the tornado watchers, they had mapped everything inside. So that is well understood. Okay. Whereas a black hole inside is impossible to understand because you have no access. You can only understand it outside. And it is only those phenomena which we observe from outside we can compare, right? Because the inside of a vortex is standard fluid mechanics.
Okay, sir. Sir, there is a action question by an undergraduate student, I think. I am showing the question in the description box. You can see it.
Sure, sure. Yeah.
So does
Because every
every
black
black
hole
hole
contains a
contains?
singularity. Yeah, very good question. What we define a black hole as is a star which has collapsed to form first a horizon. When the star collapses, first it forms a horizon, and then if the collapse continues to the singularity. So you can say that for astrophysical black holes, that's a kind of question we always have. That's a kind of idea we always have. But if you talk about acoustic black holes, the one I have been talking about in water or in sand, then these black holes have no singularity, but they have event horizon. And in the case of the rotating one, like the sink, rotating sink, they have an ergosphere, but no singularity. So acoustic black holes do not have a singularity, but real black holes, we assume that they always have a singularity. That's the assumption. See, it's an assumption or it's kind of theoretical because I have no experimental way of testing out what a singularity is. Okay?
So there is another question,
Yeah.
and I am trying to addition. Sir, we all know that in I also read in some books that special theory of relativity act as a coordinate symmetry. Am I right, sir?
Coordinate
No,
symmetry.
in
No,
the
that's
point of
not.
view of symmetry, I don't think so. That
If you say that it's a space-time symmetry, then you're right. It's a
yes.
space-time
Space time
symmetry.
change. Sorry,
Yeah,
coordinate symmetry
yeah,
is not.
space-time.
So
See,
special theory of
coordinates have no
relativity.
physical. Yeah,
Hmm,
it's a space-time symmetry. That is
okay.
correct.
Yes.
Absolutely.
So there is an analogy we can draw that the special theory of relativity is a result of space-time symmetry. So
Yeah,
in general relativity, can we draw the same thing that
yeah,
symmetry
yeah. It,
analogy
it
in
is.
general
It
relativity?
is. That's right. It is also a space-time symmetry, but it's a different kind of symmetry. It's a little more subtle. See, the reason is okay, so there are several ways of talking about it, but the reason that the first thing we would like to talk about is the fact that in special relativity, the word special means that you are restricting observers to be only inertial observers.
Ideal case,
By,
actually.
yes, by inertial observers, I mean all observers who are either at rest with respect to each other or moving with constant velocity with respect to each other. Now, in general relativity, this is precisely the restriction which you give up. So now you're talking about all observers, not just inertial observers. You're also talking about non-inertial observers. Okay. Now, of course, when you talk about non-inertial observers, that's a huge jump. That's a huge jump. And of course, then the symmetry considerations will be much more different. But there is of course, symmetry consideration all over the place. So the short answer is yes. General relativity is also about space-time symmetries, but a different kind of space-time symmetries, which are much bigger, if you wish, much more general than the symmetries that one deals with in special relativity. Okay,
So does
so
the
if special,
singularity is destroying the symmetry?
no, the singularities. See, this is the work of Raychaudhuri. Earlier, people thought that the singularities happen because of certain symmetries. The whole point about Raychaudhuri equation is that even if you did not have symmetries, okay, even then there will be singularities in general relativity. So he is talking about a much more different, much more general kind of approach. So now here I'm talking about symmetries of the space-time. Symmetries of the space-time meaning what we call symmetries of the metric. Even if there were no symmetries of a metric, the Raychaudhuri equation is so powerful. See, that is why people used it to prove the singularity theorems. The Raychaudhuri equation does not need symmetries because it is describing to you the behavior of trajectories of particles. It does not talk about the solution of Einstein equation. Einstein equation is such a hard equation that it can be solved only if you impose certain symmetries on that equation. Otherwise, you have a horrendous difficult solution equation to solve. When you impose certain symmetries, then the equation simplifies. So at that time, a lot of people thought that it is because you're imposing these symmetries, singularities are appearing in the black hole solutions. But Raychaudhuri showed that this is not true. even if there are no symmetries, there will still be the singularity in a black hole.
Okay, sir.
And this is absolutely a remarkable piece of work.
Yes, obviously, this is very much interesting. So we have one more questions left.
Yeah,
It is from Sostik Dash.
yeah, yeah.
The question is in the description box. You can see. How do we get information of black holes like radius, mass, density, etc.?
Oh, see, if you look at a black hole from outside, the space-time outside a black hole looks very much like the space-time outside a sun. And of course, you know how to determine the radius, the mass, etc. of the sun. And once you know the radius, the mass, etc., well, the question of density is a little tricky. Because when we talk about density, we are talking about what is happening at a point inside, right? That is tricky because even though a black hole has mass, the matter inside the black hole has gone to the singularity. So a black hole is not a material object. A black hole is pure gravity without matter. It's just pure curvature. There is no matter inside. So then question of density does not arise. But you can talk about mass. Why? See, because the way you talk about charge outside a sphere, you can say that this one has a charge, so Q, without knowing what is inside from Gauss's law. That is what Gauss's law gives. So similarly, by looking at the curvature outside, you can calculate the flux of the curvature and then talk about the mass or energy. Mass and energy are the same. So mass, radius, all these things are known. Radius arises, it's called the Schwarzschild radius of the black hole. It's the radius of the horizon. That arises as a part of the solution. It's parameter in the solution. Okay. Now, experimentally, if there's a single black hole sitting there, then you can't tell anything about it. But I showed you this picture of a binary, right? There's a blue giant which was forming an accretion disk around the black hole. Now, when the accretion disk happens, when material accrete into the black hole from the blue giant star, from the star outside, then very close to the horizon, they give off X-ray emission. They undergo X-ray emission. And some of this X-ray emission we can observe. Okay? It is through this X-ray emission that by studying this X-ray emission very, very carefully, we can say that yes, this is a black hole of such and such mass. Another way, which was given the Nobel Prize last time, is that if the black hole is too large, you will not see the accretion. But what you will see is the behavior of stars around the black hole. So you know that in the Milky Way, there is a gigantic black hole sitting at the center. So what these two people, this lady, Genzel and Genz, they did, Genzel and Genz, what they did was to look at, to map the trajectory of a star going around the center. And they found that this trajectory would not be that of a freely moving star. There had to be something very massive sitting at the center. So by studying this trajectory, they were able to predict the mass of what is sitting at the center. And the mass was so big that it could not be a star, it had to be a black hole. Okay, so there are these ways of saying it. I actually gave this talk, about the Nobel Prize, last Nobel Prize. That is another talk. I've given that talk. It's, I think, on the YouTube. You can check that. Okay, I think it's called Black Hole Mysteries. It's on YouTube. I've discussed it in detail. Yeah.
Thank you for your wonderful lecture. There are no questions. If we have any questions, we will mail you the questions.
Absolutely. And absolutely, Orijit. Thank you very much. It was wonderful being here and talking to you. Thank you. Thank you. Bye-bye.
And we hope we will get you for future in our programs also.
Absolutely. I have interest in solar energy. So if you're interested in solar energy in addition to physics, if you talk about solar energy, I'm very happy to talk about it. Okay? Oh,
thank you, sir.
Bye-bye now. Bye-bye.
Yes, sir. Have a nice day.
And you too.
Thank you, sir.
Thank you.